Welcome back everyone to the channel. So I hope you all are doing good. And today's problem is from Newton's laws of motion chapter, and I have taken this problem from Supernova physics book, and it's a quite interesting problem, I guess. So the problem states that a small coin of mass small m rests at corner A of the square tabletop with side length d shown in the figure. A fishing line is fixed at one end of the table at corner B. Then the string is passed over the coin to the corner C of the table, led through a fixed eye bolt. Pull the free end of the string very slowly until the coin finally falls off the table. The sliding friction coefficient between tabletop and the coin is mu. Elsewhere the friction is negligible. Find distance between B and the point where the coin fall off the table, and a figure is also given. So let me first explain the question in brief. So what actually they are telling is there is a tabletop ABCD, as you can clearly see, and all the points are fixed obviously. And here was one small mass of n, a coin of mass small m was initially at point A, and we have fixed a rope something like this, right, from B touching A and then finally going to C, and we are pulling out this rope at the corner C. So obviously the coin will come out from corner A. So it will follow some trajectory, unknown trajectory, we are not sure how it will come, and at some given instant they have shown the position of the coin. Let's say it's here, and this is the thread passing over the coin from corner B to C, and obviously it will after some time reach the edge BC and it will fall off the table. So let's say somewhere here the coin will finally come, and this one will be the thread. At that instant we are pulling from corner C, and the coin will fall from this point. So we are asked to find the distance from corner B, at what distance the coin is falling from the tabletop. So this is our target, to find this distance, right? So I hope the question is clear to everyone. Now we'll proceed into the solution. So let me draw the diagram again here. Let's say this is the tabletop and this is A, B, C and D. At some instant the coin is, let's say, here, and this is my rope, and I am pulling out this rope at corner C. So as it's a single rope, the rope will have same tension at every point. So I will just mark the forces on the coin. So this side of rope will exert tension of, let's say, T on the coin. So this side of rope will also exert the same tension T on the coin, right? So this was my coin of mass M. So this is at some general instant. So the net tension, I mean the resultant of these two forces, will obviously be along the angle bisector of these two lines, as the magnitudes are same. It's a very common concept. So let's say this is the net tension, and as we are pulling this coin very slowly, we'll just assume that at every instant the coin is in equilibrium. So the net tension gets balanced with the friction force, right? So the friction force, this is, let's F is friction, should be anti-parallel to T net. That's when the force gets counterbalanced, I mean the T net and friction. So let's assume this angle theta and this one as theta. Obviously these two will be equal, as I have already said that T and T both are equal in magnitude, so T net should be along the angle bisector. And from the direction of friction we can conclude that, as we know that the direction of friction must be anti-parallel to the direction of relative velocity of the coin with respect to the tabletop. So the coin must move along the direction of T net, or in the direction, or we can say in the direction opposite to friction at this instant. Let's say its magnitude is V, and I have shown the direction along T naught or opposite to F, both are same actually. So this is my diagram at any instant. Now let's mark this point as P. Now what you can conclude that length PC and PP both will change with time. Okay, so what you can call about rate of change of PC length, right? So d of PC upon dt, we can write it as, or let's put a minus here because PC length will decrease with time with a magnitude of v cos theta, as this v is along t net, so along PC velocity will be v cos theta. Similarly along PB also velocity will be v cos theta. So similarly we can write minus of d of PB upon dt will be v cos theta, right? So now we can, let's name this equation as equation number 1 and this one as equation number 2. Now I'll simply subtract one equation from the other, so I'll get minus of dpc dt plus of d of pb dt will be equals to 0. Now just from simple manipulation I can write d dt of pb minus pc, this is 0. So basically PB minus PC is constant throughout the motion. That's my major conclusion, right? Because that will immensely help for the further solution. I'll tell you why. So P is an arbitrary point, and basically P, the location of P will denote the trajectory of the coin. So PB minus PC is constant. Now you just recall from coordinate geometry that when a arbitrary point is moving in a plane in such a way that the difference of its distance from two fixed points is constant, what we call it? We call it a hyperbolic trajectory, right? If the sum was constant, we would have called it an elliptical trajectory. So this is nothing but a hyperbola. I mean the locus of P is hyperbola. Let me write like this: locus of P is hyperbola. That's why I've said that this conclusion will immensely help in our solution, right? So now I think it's quite clear. Let me mark the length here as d. It was given that the sides of the squares was d. So initially the coin was here and it was following some hyperbolic trajectory and it has come to here. Then finally it will cross BC, let's say somewhere like this. So we are just trying to find out this length. Now I will draw all the figure in a standard hyperbola form, right? Let me take the hyperbola. Let's say these are the coordinate axes as x and y. This one is my standard hyperbola. I'm taking x square minus a square minus, sorry, x square upon a square minus y square upon b square as 1. This is my hyperbola. And this is obviously the x-axis and this is obviously the y-axis. So, and from here we can conclude that B and C are the locus, right? Sorry, are the focus, right? These two are the focus of the hyperbola and P is some arbitrary point. Now let me mark this as B and this one as C. So according to our equation, this coordinate will be AE comma 0 and this coordinate will be minus AE comma 0. And let's say this one is a square. I mean, this is a very bad diagram. At any stage it is not looking like a square at all. It is kind of a rectangle. But just for sake of our calculation, you just assume it theoretically that this one is a square, right? So B and C are the focus of the hyperbola, and this distance is obviously d as given, and from our figure we can call it as twice of AE. And initially also this distance is d. Actually this was ABCD, this one, right? Yeah, this one was the square. Here also I have drawn ABCD, and this was the initial position of the coin. This one here, it was the initial, right? This one is the initial position of point at point A, and obviously this all the sides, I mean A, B, B, C, C, D, D, A, all are of equal length D. Now I'll just use two relations from the standard coordinate geometry understandings and we'll solve this problem. One is here already written, 2AE equals to D, and next now I'll use the length of AB. AB is nothing but the length of semilatus rectum, right? Because B is one of the focus of the hyperbola. So length of semilatus rectum will be B square upon A, and that is equals to D. Okay, so these two are my now equations, and I'll solve these two equations. What is my target? Actually this one is the final position of the coin, and I'm trying to find out this length, and this coordinate must be minus a comma 0, vertex of the hyperbola. So this length should be AE minus A. So my required length is AE minus A. So I can simply write AE as D by 2 from this equation. We can write AE as D upon 2, and now I'll substitute the value of A as well. So let me do one thing. For a hyperbola, we know that E square, eccentricity square, is 1 plus B square upon A square. So B square will be E square minus 1 into A square. So I'm just substituting this B square value here. So we'll get E square minus 1 into A square upon A as D. 1A and A gets cancelled, and again I'll put A as D upon 2E, right, from this equation. 1D, D gets cancelled, we'll get E square minus 2E minus 1 equals to 0, this quadratic equation. Solving this quadratic, we'll get the root, both roots as this, right? But one root will get neglected. You will easily observe why, because 1 plus minus root 2 are my roots, but 1 plus root 2 is a valid root, but 1 minus root 2 is not possible. Obviously it's a negative quantity and eccentricity cannot be negative, so this is not the correct root. We'll proceed with E equals to 1 plus root 2. So now we can easily substitute the value of A in terms of D. A was D upon 2E from this equation, right? A was D upon 2E. So we'll write this as D upon 2 into 1 plus root 2. Let me take D by 2 common. So this will be 1 minus root 2 minus 1. I have just rationalized directly by multiplying numerator denominator by root 2 minus 1. And after some simplification, it will end up like this. So actually this is my final answer, right? So let me mark it here, that the coin will follow some hyperbolic trajectory like this, and finally it will fall off the tabletop at a distance of D into 1 minus 1 upon root 2, this distance. Yeah, so it's kind of a nice problem, I guess, and I hope you learned something new from this problem. And so that's all for today. Thank you, and stay tuned for some more interesting problems.